Alors, bonjour tout le monde. Merci d'être là aujourd'hui. Je m'appelle Marie-Hélène Véronneau. Je suis professeure ici au département de psychologie de l'UQAM. Et aujourd'hui, j'ai le plaisir de vous présenter notre conférencier NeuroQAM du mois de novembre, donc Mickael Deroche.
Merci.
Alors, je vais vous parler un petit peu de notre conférencier. Donc, pour résumer un peu son parcours, Mickael a obtenu un diplôme d'ingénieur à l'École supérieure d'ingénieurs de Poitiers et puis une maîtrise à l'Université de Poitiers en France. Ensuite, il a obtenu son doctorat en psychoacoustique de la parole à l'Université de Cardiff au Royaume-Uni. Puis, il a fait sa formation postdoctorale à l'Université du Maryland et à l'Université Johns Hopkins aux États-Unis. Et puis ensuite, il s'est établi ici à Montréal. Il a travaillé dans plusieurs groupes de chercheurs avant d'être engagé comme professeur à l'Université Concordia. Ses travaux sont entre autres financés par le Conseil de recherche en sciences naturelles et en génie du Canada, par le FRQNT. Puis ses recherches sont vraiment très diverses. J'ai essayé de les résumer un petit peu en quelques mots, là, mais pour aller à l'essentiel, ça porte sur la plasticité du cerveau, notamment en lien avec les implants cochléaires, dont il va être question aujourd'hui. Aussi la charge cognitive lors de l'écoute, la production verbale, l'effort d'écoute dans les environnements bruyants et la prosodie dans le contexte du bilinguisme. Pas pire?
Oui, c'est un bon résumé.
Oui, super, ça vient de ta page web. Donc, pour terminer, je veux quand même mentionner ce qui n'est pas sur la page web, c'est que, donc, Mickael, il fait partie du Centre de recherche en développement humain à Concordia, comme moi. En fait, c'était un centre qui est interuniversitaire. Et puis, vraiment, je vois Mickael à toutes les...
Pour une fois, c'est moi qui viens ici, alors que c'est souvent toi qui viens à Concordia.
Oui, c'est vrai. Mais tu sais, moi, ça m'impressionne toujours parce que peu importe le sujet, tu es toujours là, tu participes, tu es actif, tu es très intéressé par tous les aspects du développement humain. Oui.
Oui, non, oui, j'aime beaucoup le développement des deux côtés, et chez les personnes âgées et chez les plus petits.
Oui, donc c'est toujours super intéressant de discuter avec toi parce qu'on peut vraiment y aller par tous les angles là, en lien avec le développement. Donc, je te remercie.
Je ne fais pas trop les adultes toute la période. Ouais, ça, je fais moins.
Parfait. Mais tu as toujours, même quand on parle des adultes, tu es là, puis c'est toujours très intéressant d'entendre ce que tu as à contribuer. Merci. Donc, je te souhaite la bienvenue, puis
merci beaucoup.
Bonne conférence.
C'est vraiment un plaisir d'être ici. Au niveau du micro, si c'est enregistré, il faut mieux que je parle devant l'ordinateur. Non, c'est n'importe où. C'est parti. OK. So I'll switch to English to describe my research, just because I'm used to it. And so this work is really conducted in collaboration with central team, some colleagues in Oklahoma City in a clinic called Hearts for Hearing. And they are seeing a lot of kids with cochlear implants. Other colleagues in Haskins Labs, ex-Haskins Labs, because that no longer exists, now Yale, and my lab in Concordia. We are really interested in outcomes from children with cochlear implants. Those devices, I don't know how much you know about them, so I'll start with a quick recap on what is a cochlear implant, how does it work, and what they're good and what they're not so good at. And then I'll try to explain that there is a huge heterogeneity in outcomes, and we're very interested in understanding why a certain kid with a CI does so well with their device and another kid is not doing so well. And so this work is really trying to go more than behavioral data, just looking into brain imaging. And this is a population that we in the past have not known very much about their brain, for the simple reason that if you do brain imaging, often you want to do fMRI. And if you have a magnet, you can't go in fMRI. More recently, they've started to make some devices that are MR compatible, except you still have huge artifacts. So wouldn't be so used for research purposes, but for clinical purposes, it could be useful. So here I'll present you two techniques that are EEG and fNIRS that we run for this project across a number of tasks. And the idea is to try to figure out something about their brain signals in low-level auditory processing, low-level visual processing, low-level motor processing, higher-level auditory or visual, and so on. A lot of those tasks can be applied to other populations of interest. If you're interested in autism, or if you're interested in dyslexia or anything, we can use the same techniques, and those techniques should come at Concordia in a second. psychology department just after Christmas. So if you're interested in using those techniques for your own purpose with your own clinical population, I am more than happy. I'm open for business. I'm more than happy to collaborate with you in different research questions unrelated to cochlear implants. Okay, so quick recap. What is a cochlear implant? Any of you has an idea? Well, I know Franco would know and you would know, but do you have an idea what a cochlear implant is? This is the first time you hear about cochlear implants. More or less? Yep. So a cochlear implant is fundamentally different from a hearing aid. You know, if you have hearing loss when you get older, you can go to the pharmacy, well, not in here in Quebec, in the US, you can literally go to the pharmacy and get a hearing aid. And all it does is just amplifying the sound where you have loss. So if you have a loss of 40 decibel at 4,000 hertz, we amplify the sound by exactly that amount. But it still relies on the fact that your hair cells are going to transduce it into electrical current. In the case of cochlear implants, the hair cells are no longer working, so we completely bypass transductions and we stimulate directly. We are shocking, we're sending electrical current in the auditory nerve of patients, and instead of feeling pain, they hear sound, because that's what the brain does. If you give it an electrical signal, it uses it, and depending on whether they are auditory neurons or visual neurons and so on, you'll have different percepts. So there are two parts in an implant. There's a part that you will be able to see externally. So that part is very similar to a hearing aid. You have a microphone that picks up the sound, sent to a speech processor. This is where we can do all sorts of signal processing stuff, engineering like noise cancellation, source localization, so on. And then we need to go inside the skull. So to go inside the skull, we'll move to like megahertz, like cell phone frequencies. So this is a radio frequency transmitter, and it goes, not too far, like 2-3 centimeters away. And inside the mastoid bone, we've encastrated radio frequency receivers. So you have a little sort of cell phone inside your bone, picking up the frequencies that we've sent just outside. So this is a magnet. So you can take it off and you're deaf again. And so every night the kids take off their CI, they're deaf when they sleep, they wake up, they put it on, hearing comes again. And so this is now decoded from cell phone to normal frequencies and then converted into electrical current that is sent through the array of electrodes. So this is the array of electrodes. Each little bar here is an electrode, and we can send different electrical currents, different information to each of those electrodes. So what we'll do is that we'll do some sort of Fourier analysis, divide the spectrum of frequencies into many different bands, and then each of those electrodes can represent different frequency bands. And so by doing this, we're able to approach a little bit of speech information. It works remarkably well for speech as long as the environment is quiet. It really doesn't work very well for pitch perception, because for pitch particularly, you need an information called the temporal fine structure, which isn't delivered in a cochlear implant. So CI users, CI stands for cochlear implant, they're notoriously bad, or they don't enjoy very much music, but even for speech, anything that is related to pitch, intonation in the voice, whether it's a male, female voice, whether it's a question or a statement, whether the person is happy or sad, all those things, those suprasegmental features of speech will generally not be well transmitted. So there's a lot of deficits even for speech, but certainly for things that are more music related, they're really not very good. For a number of reasons, one of them, the fact that we are not able to go all the way at the apex of the cochlea. This is real size cochlea. It's a very tiny structure, holds in the tip of your fingers. And we're not able to go all the way at the apex, even with very thin electrodes. The top of the cochlea is what you need for speech and for music. That's where the low frequencies are. So that means we're shifting all the frequencies. There are a lot of reasons why pitch would not be well transmitted. I'll pass through the aspects of surgery. It's heavy surgery, so there are real questions. There's a video, if you're interested, maybe after the talk, I could play it to you. It's a bit gruesome. For a kid who is born deaf, going through this sort of operation at 6 months is not easy for parents to make that call. You open the brain, it's something that you need to consider. But the literature on the subject really suggests that we should try to implant as early as possible. And here is generally the sort of data that you would get. So in terms of outcomes, this is the sort of the catchphrase in the field: earlier the better. If you are plotting here on the y-axis a measure of this is called the infant toddler meaningful auditory integration scale, because at 1 year of age or 2 years of age you can't assess language development very easily, so you need some sort of precursor measures. So this is a structure interview that assess vocalization behavior, alertness to sound, deriving meaning from sound. So regardless of exactly how it's measured, think of it as language development at the early stages. And so you have the normal hearing range here, and plus and minus 1 SD. And this is what sort of outcomes you would get in a cohort of kids who have been deaf for 1 year and then implanted between 1 and 1.5 years of age. So before the implants, they're generally very, very low, otherwise they wouldn't be eligible to receive a cochlear implant. But after 3 months, it's already back to 50, 70%, and 6 to 12 months of age, they retrieve scores that are in par with normal hearing, the normal hearing range. So this is really impressive. That means, 1 year after the implantation, you almost behave like a normal hearing child. If you look at a different cohort, now being implanted slightly later, this is not much later, just like 1.5 to 2 years old, you find the same sort of slope. So within 1 year after implantation, they still catch up very quickly. However, their asymptote a little bit lower, and that asymptote actually starts to be beyond the normal hearing range. And if you look at a cohort even later, then you start to no longer see the sort of steep slope that we get. There's a lot of individual variability, and the variance starts to be not explained so easily by this age at implantation or the duration of experience with a CI. So the literature in the field of cochlear implant is very adamant that implanting earlier is better. And it's true for oral language, it's true for communication. For certain aspects, like pitch, for example, that might not be true. But for general development, it seems to be the case. But there's a lot of variability that we're not able to explain. So this is what we are after, trying to better understand why there are such diverse outcomes in this population. We know that age at implantation will be critical. It was almost felt in advance, like before implantation was quite common. People thought that if you implant an adult who's been deaf for 60 years, you're going to get no benefit because of the critical period. And now more and more people are like, well, actually, it's never too late. The brain is always able to get some information and retrieve something, even if you've been deaf for a long time. So even the idea of sensitive periods has very long tails. So duration of CI use could be useful if you are looking within 1 year post-implantation. But if you're looking at only users that have at least 1 year of use, generally that's not a factor that really makes a difference because it's sort of plateaued at this point. Device related, that means, whether you go with the manufacturer Cochlear or manufacturer Advanced Bionics or Neuralink, or you will have some differences because they start to do slightly different signal processing, as well as surgical parameters. A lot of people are interested in medical aspects. Some surgeons are better than others. Some use robots to insert the electrode array at a constant speed. The cochlea has two sort of points. There's a force here that can tear apart the tissue, cause bleeding, and then the second turn here also can do it. So inserting the array of electrodes is not so easy to do, surgically speaking. Some surgeons use steroids that can reduce inflammation. Others don't use steroids. The skills of the surgeon from one country to another may not be the same where they're trained and so on. So there's a lot of other parameters that are irrelevant to either the child or the device, just from the fact that you go through an operation and other people are involved. Communication mode is certainly important. we think that there is always better outcomes for people, for families who are promoting oral and listening language versus visual sign language. I'll go back to this maybe after the talk because there are some debates about this. Systematically in the audiological world, people are discouraging families to use sign language, and maybe it's not so clear that it's a bad idea to use sign language. So we'll go back to this later. And there are other characteristics of the child, which you would find in many other fields unrelated to cochlear implant: cognitive skills of the child, nonverbal IQ, inherent language aptitudes. So many of those characteristics are notoriously hard to capture, and we thought that we can try to capture some of them by doing some brain imaging and seeing how they process information. So now that was just a recap on cochlear implant world. Some recap on brain plasticity. That now would be like, very similar to the work that Franco de Poré is doing, sensory deprivation in the blind or in the deaf. What does he do to the brain? The general idea is that of recruitment. If you don't use it, you lose it. Something else is going to use that structure. So, for example, in the blind, if you're born completely blind, after a period of time, the visual cortex, which is not supposed to do touch is supposed to be in the somatosensory cortex, but you will have braille reading. That will happen here. You would have auditory localization and discrimination, which is supposed to be in the temporal, superior temporal gyrus. You would have verbal memory and language, all those things starting in the visual cortex. And those are evidence that the brain is trying to find a way to, recruit resources of other stuff that are not being used in the visual cortex for different purposes. Same thing in the case of deafness. If you're born completely deaf, the auditory cortex, which is supposed to do hearing stuff, is going to start to process sign language, purely visual, but still related to language. Some visual tasks related to motion and also vibrotactile stimulation. So those are called cross-modal changes because it's examples of the brain using resources from area A for a function that is not supposed to be in this area. Now, this sort of theory is criticized, or it has limitations. Let me just finish with the slide. If we keep going with this sort of theory, the idea would be that, surprisingly, in this context, plasticity would not be a good thing. We generally think of plasticity, well, that's great. The brain is so adaptive. You happen to live in a silent world, and the brain finds a way to use resources from the auditory cortex for visual purposes, really trying to fit to the environment you live in. And evidently, the brain does not know that it cannot predict in a year from now, you'll get a cochlear implant. So actually don't change too much stuff because you'll use this auditory cortex later on. You can't predict the future. So in the case of cochlear implants, we are suspecting that maybe a plastic brain would be undesirable or maladaptive, because by the time you receive a cochlear implant, there are no auditory resources to do auditory business. They will be used for other purposes. So actually, if you happen to have a rigid brain where the brain stays in place how it's supposed to be, then maybe you get better outcomes for a cochlear implant. So this is the hypothesis of cross-modal maladaptive changes. Second, competing theory comes from the fact that, well, this sort of views about cross-modal changes is really looking at single modality. Now, if you're deaf, this is what's happening in another cortical area is going to recruit it for its benefit. But people who are looking at development in a general sense will tell you that cortical areas develop and mature from multiple senses in concert. It's not the case that each modality has its own developmental course. They are fitting with each other strongly. So if you take high-level functions such as literacy skills, it's often depicted in the form of a pyramid like this. You have reading comprehension at the top, which itself needs skills in oral language on the auditory side and skills in reading comprehension in the visual side. And oral language itself is scaffolded on top of vocabulary and even phonemic awareness at lower level. Reading comprehension
is on top of reading fluency and expression, text structures and genres, letters, sounds, and phonics, and concepts of print. So, it's a bit of a scaffolding. And when you think of this pyramid, if you think, okay, let's say that we sacrifice the whole blue part because you're deaf, there's no auditory stuff. Maybe the whole pyramid collapses. It's not the case that the visual side is going to get stronger and hold the whole pyramid together. Maybe you end up with just the whole system being out of balance. So this is really a competing theory because it does not predict necessarily that the intact modality would be stronger. You could surprisingly have something where, like, if you're born deaf, you end up with a weak visual system because the development of the visual system itself would require all the modalities in concert. And that certainly could be because language is a driver of development in many aspects. So this is generally referred to as the interactive specialization framework. And the key here is whether you look at single modality or whether you look at the fact that modalities really develop in tandem. Does that make sense for everyone? Good. So we've been incredibly lucky to be funded for the past 4 or 5 years by a foundation called the Oberkotter Foundation in the US. And I'll just read the little spiel that they have so that you can get a sense of what the goal of the foundation is. The work of this foundation has always been driven by the trustees' passionate belief that all children who are deaf or hard of hearing should have the opportunity to reach their full potential, whatever this means, emotional, social, psychological, their full potential, not just academic outcomes. The Oberkotter Foundation focuses this effort on supporting families who have chosen listening and spoken language for their child. I highlighted this part because, this is quite key. It's saying we're not quite supporting sign language. We want families who are, supporting the kids into listening and oral outcomes. And opportunities for children to develop social, emotional, language, and educational skills. So to produce the best outcomes for every child and to capitalize on the critical stages of cognitive and language development between birth and age 5. So lots of things happening in the first few years of life. If you miss the train, something like you're going to have deficits that will be hard to catch up later. So we recruited, and I'm going to present, it's the same cohort across the whole talk. 75 children, 50 of them have cochlear implants, and 25 as a control group for normal hearing. Now, within the 50 that have cochlear implants, we took 26 that have very good language, and this is evaluated with this measure called the Clinical Evaluation of Language Fundamentals, 5th edition. And it gives you a score normalized by 100 if you have normal language. One standard deviation down, you're up to 85, and so all the kids that are in blue here they are worse than 1 standard deviation from the norm, whereas some kids with CI are actually in par with normal hearing kids. Okay, now they're between 7 and 18, but we still capitalize on 0 to 5 years old because all of them are implanted before their 4th birthday. So they're implanted quite early in life, some of them very early in life. And we're interested in whether the brain is able to reverse some of the changes that have happened due to sensory deprivation. Okay, other differences in this population. The first thing that is interesting is a slight difference in age at hearing aid fitting. If the families realize that the child has hearing loss, they can seek audiological help and then be fitted with a hearing aid. You generally try this before you get to be a candidate for a cochlear implant. However, in most of those cases, the hearing aid is utterly useless because there are no hair cells, they've disappeared. So you're trying to amplify the sound, but the strong transduction is not happening so well. So you get very little input anyway. So shortly after you get a hearing aid for maybe 1 year, then you move to the cochlear implant. But what is different? So, and here there's about 10 months difference between the kids with good language in red on average and the kids with poor language. That 10 months difference is almost meaningless since the hearing aid is not really active, but it tells you something about the families of the kids with good language being proactive in seeking audiological help and looking for a hearing aid 10 months earlier, the family of the kids with poor language. The difference in terms of first at implantation, that is now very relevant because they truly get hearing, is about 7 months. So 7 months is not a ton, but 7 months is huge at the group level between the kids who do super well here on the top, red, and the kids who don't do very well with language on the bottom. But interestingly, there is no correlation between self and age at implantation. So even though at a group level it could be useful, and that very consistent with the literature, it does not really explain individual viability. We need better predictors. A little check on audiological outcomes. The first thing that you can suspect is, well, maybe the kid hasn't been well fitted. When you're tuning your cochlear implant, you're increasing the level of electrical current. Can you hear something? Can you hear something? Okay, that's your threshold. And then you bump it up all the way to like, oh, this is painfully loud. Okay, that's maximum. And then we set up a range of electrical current. We don't want to, be painful to the kid. So there is a range that's called mapping or fitting. And so here we're checking that all the thresholds that you get through audiometric frequencies would be between 20 and 30 dB HL, which is quite common in the field. Well, the fact that normal hearing have better, that's not very surprising. They have normal hearing after all. But what's interesting is that what's critical is that there's no difference between the poor and the good CI kids. Okay, other stuff that is routinely measured in the clinic when you get implanted is things like speech intelligibility. So consonant nucleus consonant words. They can be measured, first of all, in quiet. Often they're tested in one ear, then in the other ear, and then in both. All the 26 kids who have good language were implanted on both sides. And a majority, I think 19 of the 24 were implanted on both sides as well. There are only a few who were unilaterally implanted. So this tells you what they do, how well they're doing with their CI. In quiet, they all understand on average above 80%. So that is generally the outcomes that you get. A kid born deaf, you can have a conversation with that kid in the corridor if it's quiet without doing any sign language. They'll understand you because they understand beyond 80%. The fact that it's slightly better actually in the right ear than in the left ear is called the right ear advantage in the field. And it's thought that because the right ear projects to the left hemisphere who process language, there is a bit of an advantage in implanting the right side versus the left side who projects more towards music and so on. So now, whether it's truly a right ear advantage or whether it's a belief, because since surgeons believe that the right ear advantage is real, they tend to implant the right ear first, which means the right ear becomes dominant, which means they sustain the belief that the right ear advantage exists. So whether it truly exists or not, I'm not entirely convinced, but generally you would find the right ear being better than the left. When both of them, now you're looking at bilateral advantage, there is surprisingly the good language kids are actually getting slightly more benefits than the blue ones, but it's really a side note. Not surprisingly, those sort of speech intelligibility, this is more like word intelligibility scores, correlate strongly with language scores. Language is a lot more global, whereas this is really auditory. But there is no correlation in the good language because they're largely at ceiling. Same thing when you look at now sentences, often used in the US, the material called AZ Bio, and measured in quiet or plus 10 dB SNR, plus 5 dB SNR, and you find that the kids with good language, they outperform the kids with poor language in quiet for sure. And what's interesting as well is that they seem to be more robust to the presence of noise than the kids with poor language. So you can think of top-down influence, like if you have better language, you're better able to fill in the gaps because there was noise present. And so you sustain the presence of noise better than if you have poor language skills. Again, very strong correlation with the language outcomes, but not in a good language group. Okay, other factors that are generally not looked at very closely, and they deal with how supportive or nurturing the environment may be. we looked, because we had access to the data with the clinic, at how diligent the parents are at attending to therapy appointments or to audiology appointments. You generally have both audiology appointments for hearing and then speech therapy to get the speech going. And there is a strong correlation between the speech intelligibility scores, whether they're word or sentences, and attendance to those appointments, as well as how much they use their CI in a day. Some kids are only turning the CI on for 6 hours per day. We have access to those data because it's logged directly in the device, a bit like a Bluetooth, and you can know how often, how much time was the CI on during the day. And other kids, they have it for close to like 16 hours a day. It's just literally they have it all the time except when they sleep, and then they need to recharge the battery. But and that really seems to make sense if you're looking at just like how much speech exposure is happening. Well, if you have your CI on for longer periods of time, you're going to get more speech for sure. So this tells you about the quality of the environment that those kids benefit from. So a summary of those sort of outcomes that are really more on the neurological side is that children with better language abilities had better speech perception. Not surprising. This is true for isolated words, perhaps gaining more bilateral advantage, true for sentences, and more robust noise in the background. And this isn't just explained by their age at implantation. That is only relevant at the group level, but it might be influenced by a range of environmental factors, how supportive, how nurturing the environment is. And there are much more work to be done on these environment factors. There are studies showing that CIs don't work as well for poor people as they do for rich people, because it's not that the device itself is different. It's just that the quality of the environment at home will depend to some degree on factors about what's happening at home, how much speech exposure is happening, do you read to your kid, and so on. Plenty of stuff that we're not really capturing that would require a lot more sort of social work, like invading the private home space and seeing what's happening. Okay, how about the literacy skills? Let's move towards more academic goals, do they succeed well at school? So we used this battery of tests called the Reading Inventory and Scholastic Evaluation. And this battery has 6 subtests: word decoding, vocabulary, morphology, sentence processing, efficacy of reading and reading and comprehension. And what is very clear here is that the red data points are all on par with normal hearing. So you can be a kid with a cochlear implant and have normal literacy skills. And the kid with poor language were only implanted just 7 months later on average. They're really suffering in all those aspects of literacy skills. And literacy per se does not have to be related to audition. It could really, it's very close to it because it includes language, but it could use other modalities like reading skills. It's not necessarily intuitive that it requires good hearing. If we're plotting now individual data points in terms of their chronological age, you're finding that rise scores increase with age because that battery is not age controlled for. What is really key here is that the blue, the slope for the kids with poor language is actually shallower. So if you think of the slope of this linear regression as how fast cognitive maturation is happening, it is happening more slowly for the kids with poor language. What is really interesting is that the red line is actually steeper than the one for normal hearing. The kids with high language who are going to the audiology clinic 3 times a week and doing speech therapy and people on their back putting their device on, they're on steroids in terms of language development. And so this is really amazing. It shows you the sort of benefit that clinical work can do when you are behind the kid, just pushing to maximize what he can get from the implant. And what's interesting for us, at least in terms of rationale for doing brain imaging is that this RISE scores, literacy skills, is not predicted by age at implantation. So again, if age at implantation is a relevant factor for a group level, it does not really work on individual basis. Now, we also happen in this RISE battery to have normative data on thousands of kids at different grade level, from grade 3, 7 years of age, all the way to grade 12 at 18 years of age. And so the normative data are here, those gray bars. You see the 25 percentile, no, that's actually 95, the 5th percentile, like 2.5 percentile. And the slightly more gray zone would be 50% of the distribution. The median would be the black bar. And so the whole square here is 95%. What is quite key is to see that some of those many of those blue dots, many of those kids are lower than the 95 percentile of the normative distribution. So in all those tests, word decoding, vocabulary, sentence processing, etc., many of those kids are scoring outside of the 95% of the normal hearing population. But many of those kids with good language in red are doing better than 95% of the normal hearing population. Once again, set up on steroids in terms of language development and literacy development. So this is, a testament of like the remarkable benefits that kids with cochlear implant can get if you're doing a good job at pushing them. Okay, so what could cause such extremely opposite outcomes between kids with good and kids with bad language when they have a cochlear implant? We think that we could find the answer by doing some brain imaging in a number of different tasks. So we're going to do EEG and FNIRS. And I'll repeat it, those are the same, not exactly the same two systems, but we're going to have those systems in the psychology department at Concordia. If you're interested in those for other disorders, come and see me. I'd love to talk about it. So our EEG is a 128 high density, so-called EGI system. I'm not going to re-explain what EEG is doing, but you're measuring cortical potentials at the scalp. And then if you're interested in doing some source localization, you can try to figure out where is this activity coming from, because you're only measuring at the scalp, but it comes from neural generators deep down. And in FNIRS, this is based on light. Okay, so it is almost like fMRI. We're trying to get at the bold response. But instead of using magnetic resonance, we're shining light. Now, if you take a flashlight and you shine light through the palm of your hand, you'll see a little red dot there. Line is going through your tissue. And depending on whether you see the red dot slightly orangey or slightly reddish, you can actually infer how much oxygen was in that tissue. And from how much oxygen was in the tissue, you then deduce how much neurons have fired for the neurovascular coupling to happen to bring so much oxygen there. So it's a bit of a convoluted technique, if you will, but I'll demonstrate that it works. And so in this case, so each red dot is a source of light, LED, just shine light there. And light scatters a little bit through the brain. It doesn't scatter super far. So, it does, like you could try to measure it from this detector, the source from the light from this guy, but you will get like such little signal that it's very difficult to get something. So the only detectors that are useful are generally the ones that are adjacent to a source. So those 3 detectors for this source, those 4 detectors for this source, and so on. So we put a few more source and detectors close to the temporal regions because we're more interested in this, where the cochlear implants were. So we have a total of 122 channels from those 39 sources and 31 detectors. Now, one thing I'll mention just on this montage, if you're familiar with the literature on FNIRS, you may see a lot of papers when they just only look at a ROI. I'm looking at motor processing, I'm just going to put my montage to do this. That is, in my view, a mistake, because what I'll show you here is that there's a lot of things happening outside of the region of interest. And sometimes those are more important and more predictive of outcomes like language than the region of interest, where it may not show group differences. So it's actually quite good to have the whole head montage. But what's some of the limitation of FNIRS is that you can go very deep. You're like limited to maybe 3-4 centimeters. So you're not going to look at the hippocampus with FNIRS, but you can look at visual cortex, auditory cortex. Yes, as a whole, probably not A1 because it's deep in the sylvian fissure, so like it's quite deep. But auditory association areas you can certainly measure. Motor cortex, frontal lobe, you can measure stuff. And so you get, and it has advantages over fMRI because you get 2 independent signals for HBO and HBR because you're looking into 2 different wavelengths of light, of infrared light. So I won't say much more about the technique themselves. If you're interested in knowing more about FNIRS, we can talk about it more. Okay, and here is a depiction. How am I doing on time? Okay, good, excellent. Here is a depiction of all the tasks that we've done with this cohort of kids. So we've looked at low-level visual processing. There's a lot of literature, especially like in deafness, on the checkerboard. Type checkerboard, plasticity. Plenty of people have done checkerboard papers. So this is a checkerboard that appears on the screen and then rotates to its mirror image a number of times. We've done low-level auditory processing, typical, an audible paradigm. Sometimes you have a deviant sound from a standard sound. And if it's deviant and your brain was making auditory expectations about what they're supposed to listen to, when a deviant comes, you have a bit of a signal, like a surprise signal. Oh, this is not what I expected to hear. So, by doing this task, we're trying to prime whether their auditory brain is, alive. We're doing now higher forms of visual and auditory processing by now showing words or non-words on the screen. So it's still visual processing, but higher level than a checkerboard. And same thing in the auditory domain. So words or non-words, but played loudspeaker. We're doing low-level motor processing. You are squeezing the joystick of the back triggers of a joystick. In fact, the joystick vibrated or not. There's also a bit of somatosensory processing involved in this. We're doing AV integration with the MAGERC stimuli, except we don't do incongruency. It's just A alone, V alone, or AV together. Just looking at AV fusion. Do you get like a benefit of multimodal processing? And we're also doing resting states, either with a typical Inkscape video. If you're familiar with a resting state, that's a video that has audio as well into it. And we're also doing 10 minutes of the Despicable Me because it's fun. No, but it's just to like also look into like emotional networks. So we have certain parts within the movie that are more emotional. If you remember when Drew is reading the little story to the 3 kids, that's part. So that's it. The plan is to try and tell you a little bit of it. I'm probably not going to speak much about the resting state because for sake of time, there's a lot to speak about. And this is definitely, a bit more, it's complicated. You do network analysis and so on. So if you're interested, I have a few slides later on, but I'm just going to try to talk about the other ones that are a little bit easier to grasp. So this is typically what we had. That's the NearScout system from NIREX with the 39 sources, 31 detectors. And the loudspeakers here are not playing anything. It's just for the other task, but you were just looking at this checkerboard rotating. And what you might see with FNIRS is something like this. So this is 0, and the checkerboard starts to be on now, and you have patches of red coming, which tells you that the brain at this time has called upon oxygen to come in those regions. And so it's a little bit like a bold response. And so you get this kind of thing. This is with all the population, 75 kids. And it's pretty clear that there is an increase here in red in the HBO signal, oxygenated hemoglobin, and you have a decrease in deoxyhemoglobin signal. So FNIRS can successfully tell you that you use the visual cortex in a visual task. Not super interesting at just this point, but if you split across the 3 groups, what you're finding is interesting stuff. So you see some differences here in the 3 groups in both HBO and HBR signal. This is directly like the color is like directly the t-value statistics, but I'll just show you the waveforms, because you might be more, you might find this more intuitive. It's like a bold response. So you have an increase in HBO, a decrease in HBR signal. And this is in V1, V2. And so, unfortunately, there were no group differences in this visual cortex, but we wanted to look deeper in there. And what we found was all those columns are different regions around the visual cortex. So this is just V1, this is V2, this is lower visual regions, this is more towards the IT cortex, and this is towards parietal regions. What's interesting here is that the kids with low language have a strong activation at V1 compared to the other group, but then this activation really dissipates very quickly as you go more peripheral visual regions. The kids with high language or the kids with normal hearing seems to not have such a strong V1 activity, but that activity being more spread in peripheral areas of the visual cortex. So despite the fact that we don't have group difference here, we think that there is a difference in the spread of the activation across the visual cortex. Now, what's also very interesting in this case, we're trying to look at whether the auditory cortex would be recruited to look at a checkerboard, which it should not. It's a visual task. The auditory cortex should just, switch off and do nothing. And it does exactly that for the CI kids, but for the normal hearing, we actually have a deactivation of both STG and MTG, superior and middle temporal gyrus. Not only that, the more you deactivate this middle temporal gyrus, superior temporal gyrus, the better your language scores, self scores. So it is a good sign. It's a modest interaction, only 6% of the variance is being explained. But the more you switch off your auditory areas in a visual task, the better your language. That tells you that, okay, it is not that, the auditory cortex should just switch off. No, it probably consumes energy just by, being alive, and you're better off trying to switch it off to focus on visual processing. That was in the FNIS part. In the EEG part, same task. What do we see? What we see is a so-called pattern onset VEP. If you have a gray background and something appears on the screen, the brain just gives you a little signal. It's not a little signal. 10 to 15 microvolts is actually quite a large signal as far as EEG is concerned. And interestingly, here, the blue waveform, the kids with low language don't have a very strong pattern onset VEP. This is very controversial. The kids with low language had later age at implantation. They had more sensory deprivation, which means their visual cortex should be even more dominant. And what we found is that they end up with a weaker visual system than the other kids. Now, that doesn't make a lot of sense if you think of cross-modal changes, where the visual cortex has to recruit the other one to become even stronger. This is a lot more in line with the idea that actually, visual and auditory have to develop together, and if one doesn't work so well, it's the whole pyramid collapse. Now, in addition to this pattern onset, when it appears on the screen, the checkerboard rotated to its mirror image, and that generates other types of VEP, visual evoked potentials, that are due to the reversals. But we didn't find group differences in these reversals. Why? Because the literature suggests that pattern reversal might be generated by V1 exclusively, whereas the pattern onset has more spread neural generators, V1, V2, and other things. And so this is somewhat consistent with the spread of activation that I talked about in the FNIS part. And it shows how it's very nice to have two different techniques to be able to confront them together. On the auditory side, we have negative potentials. And the kids with low language in blue are not able to deactivate their auditory cortex as much. So this is different than the FNIS, because in the FNIS, both CI groups could not deactivate. In the EEG part, only the ones with low language are not able to deactivate. Okay, we then extract individual peaks, for example, the pattern onset VEP, and we're trying to look at whether there's a relationship with age at implantation And we found, sure enough, that the later the implantation, the weaker the pattern onset, consistent with the group difference here. And the later the implantation, the less you can deactivate your auditory cortex in this low-level visual task. So we think that there is really a mechanistic link to sensory deprivation. It is because you're implanted later that somehow the auditory and visual network are no longer inversely coupled as they should be. And also relationship to language. So if you are having a strong visual response, better language, more deactivation of the auditory cortex in this visual task, better language. In addition to age effect, the age effects are less interesting to some degree. It's the fact that in EEG, the bigger your head, the further away you are from the neural generators. So what you measure in the scalp is lower. So that's why like amplitudes of those peaks tend to decrease from 7 to 18 years of age in both hearing and visual auditory domain. We've done some source analysis to go beyond the scalp analysis. And at the time window within the peak of the occipital response, we're finding a source in the visual cortex. And at that same time window, we're finding a different source in the auditory cortex. Now, this is a bit of a detail, but it's quite, when you fight with reviewers about, no, this is two different sources. And it's not just like that, what I'm measuring at the auditory cortex is a byproduct of the visual response. And we find that there is, what's happening in terms of the auditory cortex activity is actually lateralized on the right side, not so much on the left. And it's very strong for the normal hearing population. Be mindful that when you do a power analysis like this, whether it's activation or deactivation, you'll get the same power. So it's like squared. So this is very yellow, but it's a deactivation, chances are, of the auditory cortex. So once again, the normal hearing are better able to deactivate their auditory association areas during that visual task. Okay, so this is a summary of the first task. In FNIRS, we found activation to be more localized for the kids with low language, the CI kids with low language, but no group difference or no link to language. There was, however, a lack of deactivation in the auditory cortex in both CI groups, and that was linked to the language scores. In the EEG part, there is a weaker activity in the children with low language, and the pattern onset was related to language, as well as a weaker deactivation exacerbated by the children implanted latest and detrimental consequences to self. So not exactly mirror image of each other, like there are two different techniques. One is electrical, the other one is hemodynamic, but you have a lot of intersection that help you to better interpret why is it that why I'm seeing this signal. That's because like from this point of view, the hemodynamic perspective, it's the fact that like it's drawing blood to this region and getting rid of blood in another region. So what we're seeing here is that when you do a low-level visual task, not related to language, you should not just switch off your auditory cortex. You probably need to deactivate it to try and to spare some resources. And if you're not able to do this, that means the auditory network, it's not like it's recruited, it's not activated, it's not engaged, but it's taking some energy somewhat. And you're better off trying to deactivate. And that's what the kids with cochlear implant are not able to do, particularly those with poor language. Okay. Second task, motor processing. Motor processing, they have the FNIRS. This is only in FNIRS, no EEG. And they see squeeze, they squeeze the back triggers, and then for 1 second there's a blank, and then squeeze the back triggers. There are 10. It's a block design, 15 seconds on, 15-second rest. And in half of the blocks, the joystick also vibrated. So this is the whole population. Does FNIRS work? Yes, FNIRS is able to reliably tell you that there is activity in the motor cortex here on both sides, and a reduction in the HBR signal. So that's great. How about across the three groups? Well, you have slightly different positions. It's a bit hard to read those graphs sometimes, but you have to define a region of interest. What you can see here very clearly is that the visual cortex was strongly deactivated in this motor task. Okay, we've talked about deactivation of the auditory cortex in the visual task, and now deactivation of the visual cortex in a motor task. So this is the bold response. You have motor cortex activation in all three groups. It looked like it's slightly bigger than in the normal hearing, but the group differences were not significant. What was significant was actually the visual cortex deactivation. The kids with poor language here are less able to deactivate their visual cortex. And so this is, again, like, a very strong reason why when you do FNIRS, you shouldn't just do a region of interest. If you do region of interest in this task, you do motor stuff, you only look here, and you're missing the whole important bit, which is the deactivation of an irrelevant cortical region. Why is it so interesting? Well, because the visual cortex is very energivore. It takes a lot of resources if it's on. And so, like, there's even like complicated things like blood stealing. If the visual cortex is on, it'll steal the blood to itself, making it very difficult to measure anything else outside of the brain. And so this blood stealing phenomenon is very annoying because you want the visual cortex to do nothing to be able to measure something else in the cortex. But clearly, deactivating it must spare a lot of resources to normal hearing kids and kids with CI and good language. And that's something that the low language kids are not able to do. In the bilateral STG, we're also hoping that maybe there would be something, but we saw nothing at all in the auditory cortex. And I think why we saw nothing, it's because of this blood stealing business, that if the visual cortex is doing something, it draws all the blood to itself and you're not seeing very much outside. Somatosensory cortex, I'll talk in a second. In terms of individual differences, so no group difference in the motor cortex, but significant group difference in the visual cortex, where the low language kids are not able to deactivate it as much, and a correlation with language scores. The more you deactivate the visual cortex, the stronger it is, whereas you get nothing in terms of the motor cortex. Somatosensory, as I said, in half of the blocks, the joystick actually vibrated. So we were able to probe somatosensory processing in addition to motor processing, but that made no difference. Why is it that we were not able to capture any somatosensory activity? I don't really know. It could be that the spatial resolution was just like, somatosensory cortex can be quite narrow. We did not measure it. So the summary for this task is that we found a similar activation in the motor cortex in all groups. I'm partly thinking that this maybe could change if we had done a motor task that was a bit more related to speech, like you could do altered feedback patterns or vocal production, something where like you ask people to speak. It's a motor action, but it's very related to language. Maybe we'll be able to find some group differences. But regardless, we still find very interesting things outside of the region of interest, because the way you deactivate the visual cortex being very energivore is a good thing. It's predictive of good language outcomes, and so it was reduced here in the low language group and linked to poor language outcomes. Okay. Other task, EEG only, oddball paradigm. So you hear psh, psh, psh. That's a slightly different sound, psh, psh, psh. And the standard sound is white noise, psh, and the odd sound, the deviant sound, is spectrally modulated noise. Those are not really obvious sounds. When you do oddball patterns in hearing, often people do like ta 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 ga, or like something that could be quite different. This is still noisy, like very noisy, but the psychophysics in the CI world uses spectral modulation detection threshold as well as spectral modulation discrimination thresholds to predict speech intelligibility scores. So this particular stimuli has some relevance in the CI world. This is the EEG setup. We looked at 3 regions of interest, slightly more frontal than CZ, that's the green electrodes, for the N1P2 complex, the MMN in the frontal region, in the blue electrodes, 14 of them, and then the P3 and the parietal regions in the red electrodes. So let's look into each of those things. N1P2 This is it. You have a negative deflection around 100 milliseconds, followed by a positive deflection around 200 milliseconds. That's why it's called the N1P2. And you find this in all three groups. Surprisingly, in a normal hearing kid, it's actually not as large. And this was a significant difference. So they had weaker N1P2 amplitudes. I believe that the main reason for it is because we're not controlling the loudness level on the front end of the CI. So, it's very difficult to do loudness equalization between normal hearing and CI. Normal hearing have their normal ears. CI always amplify the sound with their the CI. And so making sure that it's same loudness. And if you increase the loudness, you increase the N1P2. So there is a high chance that the loudness of the stimuli is slightly louder, which is why N1P2 is not probably a very good measure. Looking at MMN or P3 from the difference waveforms, then it doesn't matter that the amplitude is overall larger because you look at the difference waveforms. So that's why here we're more interested in what's happening in the frontal regions, the MMN, the mismatch negativity. That is a signal about your brain trying to make predictions about what's supposed to happen fairly automatically. And if it doesn't match with the expectation, you have an error signal. That will tell you that, okay, my predictions of the world is not correct. So you want this signal to be as large as possible. So here you see on the top the waveforms of the odd signal, which is the standard. And what's supposed to happen is that the red line goes below the black line within a certain time window. So on the bottom here, you see the difference waveform, black minus red. And that shows you that little dip that we call the MMN, the mismatch negativity. And you want that dip to be as large as possible if your brain is very in tuned to, that's not what I was supposed to hear. If it doesn't show any signal, that means he's not able to predict what it's supposed to hear. He's not very attuned to, whether you say ga or da, it's not going to make a difference. For him, it's just noise. It's just the same sort of sound being presented. So you want it to be large. And very clearly, the low language have a weak MMN compared to the high language kids. Both of them have CI, and the age of implantation difference is very small, but they have a huge MMN compared to those ones. In fact, this MMN is even larger than a normal hearing one. So there are group differences here and correlation with language outcomes. The stronger your MMN, the better your language. Now that I think is, if you're not interested in cochlear implants, but in dyslexia, in autism or anything, just do some tasks like this and trying to measure whether the bigger your MMN, the better your language. Language outcomes can be useful for many other fields of psychology. And so those tasks and those techniques have some potential in the clinic, certainly. Same thing whether you look at peak amplitude versus average amplitude of the MMN. There's also interesting things about the latency. The normal hearing have an earlier latency of the MMN. You want it to be as early as possible. That means that the system is responding very fast. So the fact that they're later in the low language group is also meaningful. And then in parietal regions, the P3 or the MMN are largely the same thing, but slightly different time window. MMN is earlier in the waveform. P3 is more cognitive. It takes a bit more time to develop, but it's supposed to be a little bit more attentionally driven. So if you're really not paying attention to the task, maybe your P3 won't be so good. But if you're really I heard it different. And if you engage the kid and saying yeah, that's an odd trial. Yeah, no, then you might see a difference. In this case, we use a passive task because we didn't want to contaminate the signal with motor action. We didn't want to have to do two different tasks. So this task is only 5 or 6 minutes because we had such a huge range of different tasks that we wanted to do. So we just went, for the sake of time, to trying to capture both components in the same task. And so you can measure a P3 even if you're not paying attention to it, because your brain will make predictions, and then if it defies the predictions, it will also send a signal. So you want the red waveform here, the odd trials, to generate a positive inflection beyond the black line. And clearly the low language kids, again, are not able to do it very much, but you see a positive deflection for the high language kid as well as the normal hearing kid. Very similar idea, group difference, predictive of language scores, whether it's average or peak amplitude that works, or at least there's a trend. Peak latency also, as is a trend that normal hearing have a earlier P3 latency. And what's more interesting, that we can even go beyond language in this task and start to predict literacy skills. So in these skills, how your brain is able to generate P3. That didn't work for the MMN, so we think that P3 is actually a stronger predictor than mismatch negativity, but it can predict on an individual basis. Whether you look at amplitude or the latency, it can predict to some degree your literacy skills. So again, that's true for CI, but I suspect that it would be true for other disorders. Measuring P3 in an oddball task could be predictive of literacy skills. So, summary of this task. We had a fairly well-formed N1P2 in CI children, which was good. It's often in the literature that you find that CI users don't have a very big N1P2. We think the reason why we had it is because of this loudness difference. So we were able at least to have good waveforms and reduced mismatch negativity in the kids with low language, as well as reduced P3. And what P3 offers you that MMN doesn't is that prediction of both language and literacy scores. So a very useful task to be run in a clinic, given that it only takes 5 minutes. You know, most clinicians have 5 minutes to spare if they can have access to a free EEG. Okay. Okay, I'm gonna hurry up a little bit. But I think now you see a pattern emerging. Consistently, the low language kids, having deficiencies in their brain processing somehow. So this is the typical stimuli that are used for the migrant experiments, ba or ga. Either you play it alone, audio alone, or you see the visual stimuli alone. You can tell, just by seeing it, that he's not about to say ba. He's like, this is from the back of the throat, back of the mouth, whereas this is at the lips, ba. And then you put both together. But we're not doing any incongruency. It's not like you hear ba and you hear ga and mix it up. AV processing in FNIRS, we get across the whole population here, 75 kids, activity in the supratemporal lobe for audio task, activity in the visual cortex for the visual task, and both activity in both tasks. Now, if we look at the waveforms, we get essentially, the A and AV task activating the Wernicke. We actually did not get much in the STG. Once again, I think it's because of this blood stealing phenomenon that is really vicious. If the visual cortex is on, then it sort of steals the blood, and then you can't measure very much in the bilateral STG. But in the bilateral Wernicke or inferior parietal lobe, we were able to capture some activation to A and AV, but not to V. In the Wernicke, we're able to get activation to A alone, deactivation to V alone, and because AV gets both of them together, we get negligible changes to AV together. And in the visual cortex, we get, as expected, visual cortex activation to V and AV, but not to A. In fact, it's deactivated in the A alone. But no group differences in this thing. So FNIRS suggests that kids with cochlear implants have no problem with AV integration. We found still some interesting things about age at implantation, and this may be a bit messy, it's not that complicated. The later the implantation, the less you can activate Wernicke in audio task, which you should, if you have good hearing, but the later implantation, the less this is happening. But the more you activate the visual cortex, the more you activate the Wernicke area to the visual task, which maybe it's not such a good thing. And in the visual cortex activation, the later the implantation, the more you activate the visual cortex to the audio task, which is probably not a good thing. And the later in the implantation, the less you activate the visual cortex to the visual task. So all of those are consistent with one another, saying that the later the implantation, the more you give priority over one modality over the other, visual versus hearing. In the EEG part on this task, we found something that are very similar to the checkerboard. So again, we were hoping in the checkerboard, we're like, okay, maybe that's just very low level. That's a checkerboard has nothing to do with language. So maybe we get something, but that suggests that the kids with low language have weak visual system. But once we do a task that will be language related, we're really going to see something where like they are better. They have a stronger visual system. Still not the case. The kids with low language who had longer times of sensory auditory deprivation end up with a weak visual system, which they should not. They should end up with a stronger visual system than the other guys. But it's the kids with good language have very good visual evoked potentials in response to those visual speech stimuli, and the normal hearing kids in between, and no response to the audio alone stimuli. Same thing in the parietal lobe, but slightly differences where the second peak, this P3 component, gets strengthened by the dual modality versus the unisensory modalities. So people are looking into, AV minus A or AV minus V and seeing how much you're benefiting from the AV fusions. You should get slightly earlier peaks, but not much, like, in the order of 10 milliseconds and slightly larger amplitude. This is happening at P3, the second peak, but the reverse is happening in the P1. In the parietal lobe, things that are very early are de-emphasized, and things that are slightly later in the waveform are emphasized. Then we also, within the video, realign the time at the onset of the syllables, because the video starts with, there's a bit of gesture just before the sound is actually being produced. So if you want to measure N1, P2 in response to the sound, we look through the video. We realign the time at the onset of the syllables, and we're able to capture N1, P2 in response to both A and AV, but not to V. And some differences here where the normal hearing kids were able to differentiate the two syllables. They were actually ba and ga, whereas the signals were more similar for the CI kids. So that is suggestive that the auditory system of normal hearing kids is sharper than the one of CI kids. Not super surprising, but nice to check. So the summary of this is that we found expected activations in the visual cortex to V and AV, and Wernicke to A and AV, but no group difference, no relation to self-arise. In the EEG, greater occipital activity to the good language kids versus the low language kids to V and AV. And the parietal emphasized the dual modality versus the unisensory modalities, but similarly across groups. So this entire paper, which was just accepted last week, shows no abnormal AV integration, which means that AV integration itself is probably not good enough. Like, you can show good integration of audio and visual and still have very poor language. It is probably a sufficient but not necessary condition to language. Finally, last task I'm going to talk about is words versus non-words, whether they are played from the loudspeaker or written on the screen. This task is not completely analyzed yet. I'm still working on it. But it's you find activity in the Wernicke area for listening versus baseline versus rest in all three groups, but stronger in the normal hearing kids. You find activity in V4, but not V1. That's quite interesting. FNIRS has sufficient spatial resolution to differentiate V4, like object identification and letters identification, versus V1, which is supposed to be more lower level processing, like checkerboard. So you see this red bar here versus the blue bar here in the middle is quite good. And that also seems to be quite different across the groups. We find some correlations where the more you activate the bilateral STG in response to the listen task, the better your language scores. But this did not happen for reading. The literature suggests that it should also happen for reading, but we didn't see. In the EEG part, we get essentially a N1, P2 in response to both reading and to the listen words. And we're now interested more in the difference in the amplitude between the listen, the auditory, the spoken words and non-words versus the written words and non-words. In the normal hearing, a differentiation between the modalities that is less seen in the CI users. And the latency between the two is also quite interesting. So more on this, but essentially small group differences in FNIRS. The reading has this additional challenge that you have a deactivation of V1 to more strongly activate V4. As for the EEG, it's the magnitude of the potential elicited by spoken versus written items around CZ that might inform about the priority between visual and auditory modalities, but relatively difference between whether the words were actually words or pseudo words in all the groups, at least early in that waveform. I haven't looked later because that epoch is actually 3 seconds, so there's more information later on, maybe more for a machine learning sort of project. So the conclusion is the question that most clinicians wanted to know is the auditory cortex recruited for visual purposes? If you're a proponent of, cross-modal changes, thinking of, like if you're like doing a lot of blindness studies, deafness studies, no reverse changes, just sensory deprivation, you have very strong evidence that there is recruitment. One of the earlier slides that I presented in the presentation. In those data, the evidence for recruitment is very far from overwhelming. The CI children with poor language exhibit a weak auditory cortex, which that makes sense to us, but surprisingly, they also ended up with a weak visual cortex. That is something that doesn't really make sense, but we confirmed it in the checkerboard. It is not just because it's low level. In higher level forms of visual processing, words written, it's still the case that they have a weak visual system. So somehow we think that this pattern of finding is more in line with the interactive specialization framework, where different modalities develop in tandem with one another, and you don't end up with a stronger intact modality. Best outcomes post-implantation likely occur when brain areas are more specialized while being coupled. And coupled does not mean go together. They could be inversely coupled. That is a good thing. Auditory and visual network can be inversely coupled. That is good. What you don't want is to lose that coupling such that they are undifferentiated, just working as a whole system together. That is something that is less good. And those brain measures, we find you can't find the same sort of knowledge just by looking at age at implantation. So if you are in the CI world, you'll be like, well, how much of this could we have predicted by just age at implantation? Because we have this in the clinic. And we find that a lot of this data are just not predicted by age at implantation. It really helps to do some brain imaging to predict outcomes. So the whole point here is to be able to find many of those measures, biophysical markers, and say, well, this kid is really at risk of language delays. Let's redirect our intervention efforts early on to do certain contrasts to really boost them, because we know that it's possible for language development to be on steroids from the other kids that we've measured. So if we can just detect it, chances are we'll be able to do amazing things. That's it. So there's an army of people in this project. It's just not me on my own. Plenty of people from Oklahoma City, as well as Italy, Germany, and here in Concordia. And thank you for the Overcoder Foundation.